Great, thank you, Michelle. And let's get started. Welcome, everyone, to this webinar. I guess I'm going to tell you about a few things that we've been working on recently, and I hope you enjoy it. So let's see. So let's get started. As I said, what I wanted to tell you about today is some areas that we've been working in our security lab lately. In particular, I wanted to tell you a little bit about new developments in password hashing, and then I'll talk a little bit about sort of a new approach we developed for securing program control flow. This falls into the area of what's called control flow integrity, and I'll tell you about a new technique for control flow integrity. Hopefully we'll still have some more time, and then I'll be able to tell you about other recent work that we've been doing specifically on IoT security. In particular, how do we know that IoT devices are not revealing too much information about their owner? So again, kind of an exciting area being an intersection of privacy and security. So I hope we'll get through all three topics, but if not, I guess we will schedule future webinars and we will cover whatever we didn't cover today in a future webinar. Okay, so with that, let's get started with password hashing. And let me remind you a little bit about how password hashing works and kind of the areas that we're interested in, we've been working on recently. So, of course, everybody knows, there are constant attacks on server-side password databases that result in large-scale password breaches. So I just collected a random sample. This is a very small sample of the actual breaches that have happened in the last couple of years. So just to remind you, probably you remember a few years ago, LinkedIn lost a collection of hashed passwords that they stored. Unfortunately, they simply stored hashes, SHA-1 hashes of their password. These were unsalted, and we'll talk about the consequence of that in just a minute. So that was one event that resulted in the loss of 6 million passwords. All these people had to go in and reset their passwords. Of course, when a password breach occurs, whoever does the breach is able, in many cases, to obtain many of the original unhashed passwords, and those can then be used to attack those users on other sites as well, because unfortunately, still many users use the same password at many different sites. And again, we'll talk about mitigations for that in just a minute. Then later on, a year later, there were a couple of other breaches. Again, this is just a selected list. So there was 250,000 passwords were stolen from Twitter. Evernote had an issue where hash passwords were revealed. And Adobe had an entertaining breach where, in fact, encrypted passwords, not hash passwords, were revealed. In addition to the password hints, so as a result, the password hints actually helped attackers recover the original passwords. And then furthermore, just a more recent example, in 2015, a famous, a fairly common password manager had an issue where, in fact, hashed master passwords and assaults were compromised. And again, that in some cases, that can enable what's called an offline dictionary attack, where an attacker can try lots of words in the dictionary until he finds one that hashes to the user's password, and that essentially reveals the user's password. So the question is what to do about that. And so this was just a quick survey of what's happening. The question is, how do we store passwords in a way that makes these offline dictionary attacks harder than simply just trying all the words in a dictionary? So let's talk about, how to store passwords 101. And so, of course, I hope everybody knows that you never, ever store passwords in the clear on the server. What you actually do on the server is you store a hash of the password. Here you can see the hash of the password along with a salt. The salt is denoted by SA, and the salt is also stored in the database. And then when a user submits a password for login, what the server actually does is it simply hashes the password along with the salt and checks whether that's equal to the stored hash in the database. And if it is equal, then the login is allowed to go through. So again, this is why we use the salt and so on. This is fairly common reasoning in computer security. We discussed this actually at quite a bit of length in the computer security class that we teach, which again, you are very welcome to sign up for and attend. So I'm not going to talk about the reasons for the salt here. What I want to talk about today is this question of what hash function should be using for hashing passwords. So how do we actually hash passwords when we store them in the password database? So what happened with LinkedIn is, unfortunately, they used a SHA-1 hash of their password, and in fact, the SHA-1 hash was even unsalted. So literally all they did is they computed a SHA-1 hash of everybody's password, and that's the value that was stored in the password database. When that password database was compromised, Within 6 days, almost all the plaintext passwords were exposed. So 90% of the passwords were actually revealed. And the reason that was possible is because SHA-1 is an extremely fast hash function to evaluate. So what folks were able to do is run through a large dictionary, very, very large set of dictionary of possible passwords in a dictionary, and simply try to hash each one of them until they got ones that hit values in the password database, and that enabled them to recover the original passwords. So in some sense, this is kind of counterintuitive into what's happening in computer science. Typically, we want things to run fast as possible. When we hash passwords, actually speed is detrimental to security, because the faster the hash function is, the faster an attacker can try all words in the dictionary until he recovers the user's password. So what we really want for password hashing is much, much, much slower passwords. And by the way, I should say that LinkedIn has since updated their password scheme, and now this type of attack is not going to happen again on LinkedIn. So that's at least we hope, and so that's actually good news. And so the question I want to ask basically is, what is the right way to hash passwords? And so basically there are kind of two ideas that come to play. The first one is, when we hash a password on the server side, one thing we might want to do is, instead of just using a simple hash function where we directly just give it as input the user's password, we actually use what's called a keyed hash function. So a function that, in addition to the password, also takes a secret key. The secret key itself is going to be stored in some hardware security module, what's called an HSM. So the secret key itself is going to be stored in some secure environment that attackers will not be able to extract. And as a result, if they're able to steal the password file, the password database, if they want to try a lot of words in the dictionary, now for every word in the dictionary, they have to interrogate the HSM in order to check whether their guess is correct. Now, the HSM might be rate limited. For example, the HSM might only respond to 1,000 requests a second, in which case the attacker is going to take too long to mount his attack. So definitely using keyed hashes on the server where the key is stored in an HSM is a very strong and powerful step forward. But in many cases, there is no HSM. For example, when you're hashing passwords on a laptop, or when you're hashing passwords on a cell phone, there are actually no HSMs available, roughly speaking. And as a result, we'd like to have a mechanism that is secure even if we don't have an HSM. In addition, also, HSMs do not provide foolproof security. Maybe there is some still way to recover the secret key from the HSM. So in addition to the HSM, we'd like to also hash the password using what's called a slow space hard function. Okay, so again, these are complementary mechanisms that work in tandem. If you don't have an HSM, you would just use a slow space hard function, and that would be kind of an alternative to using a keyed hash function. So what I want to talk about is, what is a slow space hard function and which one should we use? And there's been actually a lot of progress on this recently, and that's what I want to tell you about. Okay, so the first idea dates back actually to the 90s. And the first idea, essentially, again, very, very clever idea, which is to say, let's use a slow hash function. So one that actually takes quite a bit of CPU power to evaluate. And examples of that are functions like PBKDF2 and bcrypt. So PBKDF2 is actually a standard that folks can use, and it's very, very commonly deployed. For example, Apple uses PBKDF2 in many of their products. The way PBKDF2 works is essentially it slows down the hash function basically by iterating a hash function over and over and over and over again, right? So to evaluate the function, you sort of have to take your hash function, evaluate it on the password, evaluate it again on the result, evaluate it again on the result of that, and iterate that, like, say, 100,000 times or so until the final result is the actual hashed value. Okay, now, it turns out PBKDF2 does actually more than just simple iteration of the hash function. That by itself, simply iterating a hash function is actually not secure. You have to do something more, and that's what PBKDF2 and bcrypt do. And so basically what that ensures is that when the CPU is evaluating the hash function, it takes actually quite a while to evaluate the hash function. So now, in fact, when the attacker wants to try, billions of words in a dictionary, it's actually going to take the attacker quite a bit of time to try all billion words in a dictionary, or even however many words there are he's trying to evaluate, until he's able to get the user's password. So the question is, how many iterations should we do? That is, how slow should the hash function be? And typically, this would be set so that you can evaluate the hash function on a modern server about 1,000 times a second. So that means that the actual server that's doing password authentication at the website would be able to evaluate the hash function about 1,000 times a second. So a single server can handle about 1,000 logins per second. Of course, if you have higher load on your server, you would just, you would have to buy more hardware, deploy more servers to handle that load. But that's a typical parameter that one would use for determining how many iterations to actually run. Unfortunately, there's a problem with that. This is not quite secure. And the reason, the problematic issue here is that when an attacker attacks you, when they're running their offline dictionary attack, they're not going to be using your hardware. They're not going to be using the hardware that the website is running. Instead, they're going to be using custom hardware to do their attack. So, for example, they might use GPUs to compute the hash function. GPUs, as you know, are very parallel. And, if a GPU, for example, has 100 cores on it, it could actually do 100 evaluations in one step, basically evaluate 100 words in a dictionary in one step. And in fact, you can even build commodity hardware that using ASICs and so on, where the hash evaluation is even faster. And in fact, the attacker can do his dictionary attack much, much, much faster than 1,000 evaluations per second. So let me ask you, here's a puzzle for you, just so that this is a little bit interactive. Let me ask you, so if you have to guess, when we were specifically building SHA-256, if we use SHA-256 as our hash function, how much faster could SHA-256 be made to run on a custom piece of hardware over running it on just a standard Intel processor, say Intel Skylake Xeon processor? So how much faster can ASIC be compared to standard ASIC, to standard Intel processors? Yeah. So I'll let you answer this question. While you're answering the question, let me kind of explain why commodity hardware is so much faster than just off-the-shelf Intel processors. So here I have an example. So here I have a picture of an Intel processor. I just took a picture of Skylake, which is the latest Intel processor on the market today. You can see here, this is a 4-core processor, so you can see here the 4 cores. This is 1 core, this is another core, and so on. And you can see that there's a lot of other stuff on this processor. For example, there's a lot of cache that's being used here. In fact, as you know, there are 3 layers of caching. There's a memory controller, and so on and so forth. There are many, many, many components on this processor that really are completely irrelevant and unuseful when you're trying to evaluate a hash function like SHA-256. So if you think about it, the actual piece of the hardware that evaluates SHA-256 are these 4 little squares here. You notice the squares, there's 1 little square in every core. And it's just this tiny amount of hardware on the processor that's actually being used to evaluate SHA-256. So it should be very clear that if all I want to do is just do a dictionary attack, I would never use an Intel processor off the shelf because, very little hardware and very little silicon in the processor is actually used to evaluate SHA-256. So my question to you was, how much faster would commodity hardware be compared to an Intel processor? And let's see what you guys answered. So everybody says about 500,000 times faster. So you guys are very pessimistic. You think commodity hardware can be made like super duper faster than Intel processors. Well, so here's what we did. Here's what I did. I just looked up essentially how long does it take to do SHA-256 on custom hardware, and the folks that are interested in speeding up SHA-256s are the folks that are doing Bitcoin mining. And so Bitcoin miners, when you look at the processors they build, there's no memory controllers, there are no caches on those processors. All those processors do is they just kind of flood the processor with just copies of the memory control of the SHA-256 engine. So A, the engine is optimized, and second of all, it's replicated all over the processor. So you don't just have 4 engines per core, you have thousands of engines per core. And you can see that if you just go to Amazon and buy just a Bitcoin mining rig, they cost about $1,700, and their price is constantly falling. And you can see this is on a log scale it's about 50,000 times faster than just an Intel processor. So not quite as pessimistic as you guys were expecting, but still far, far, far faster. So again, if the Intel processor can do 1,000 hashes per second, the attacker using dedicated hardware can do 50 million hashes per second. So essentially, the dictionary attack is re-enabled because the attacker can run through large portions of the dictionary very fast. Okay, so simply using a slow hash function doesn't really prevent the attacker from doing a dictionary attack because commodity hardware is so much faster than the Intel processor. So what do we do? So a beautiful idea actually appeared a couple of years ago. This is this idea that's used in Scrypt. And this idea is really elegant. So the idea basically says, well, let's use a hash function that isn't just slow, that isn't just hard to evaluate, but also takes a lot of memory to evaluate as you're computing the hash function. So now, if you think about what the custom hardware has to do, it can't just use a little piece of silicon to compute the hash function. It has to use the little piece of silicon, but right next to it, it has to allocate a large buffer of memory that's needed to evaluate the hash function. So that's the idea behind Scrypt. So if I'm building dedicated hardware to do dictionary attacks now, I have to kind of, the number of engines I can lay on one chip is sort of limited by the number of memory components that I can put in every chip. And since memory is relatively large, now each one of my chips is not going to have that many hashing engines. And so we kind of have more equality between the actual website's hardware and the attacker's hardware. Again, because the attacker cannot replicate using dedicated hardware, the attacker cannot put too many hashing engines on each chip because each engine needs a lot of memory. And memory takes space on the chip. Okay, so that's Scrypt, and that's actually a fine thing to use. There's one problem with Scrypt, however, which is that in Scrypt, if you look at how this memory is being accessed as you're evaluating the hash function, it turns out the memory access pattern actually depends on the password that the user supplied. Okay, so for my password, there would be one particular memory access pattern. For your password, there would be a different memory access pattern. Now, you might have heard of what are called cache timing attacks, where essentially an attacker who is able to actually gain a low privilege control of the web server. So the attacker sits on the web server but just has low privilege access to it. Just by having a foothold on the web server, you can actually get a lot of information as to how a high privilege process is accessing memory. Okay, so basically what you're doing is you're kind of looking at how, as a low privilege process, you're looking at how the cache is being used. And by looking at how the cache is being used, you can figure out how the high privilege process is accessing memory. You can't read the password that the high privilege process is processing, but you can see how the high privilege process is accessing memory. Well, if you can do that, as I'm entering my password, you can just measure what the memory access pattern is. And now when an attacker recovers, say, the hashed password plus the memory access pattern as the hash function was being evaluated, that essentially eliminates the memory requirement for computing the hash function. Because what the attacker would do is he would just try one password after another, but he wouldn't actually evaluate the hash function. He would just kind of compute the memory access pattern associated with the hash function. And as soon as he sees that the word, say, 1, 2, 3, 4, 5 does not match the memory access pattern that the user generated with his password, he knows that the user's password is not 1, 2, 3, 4, 5. So again, he can re-instantiate the offline dictionary attack without memory just using the memory access pattern. So I hope that was clear, but essentially what it says is that Scrypt, again, it's a wonderful, wonderful idea in that it requires the attacker to spend a lot of memory in order to evaluate the hash function, but the minute the attacker has a little bit of side information, in particular the memory access patterns as the hash function is being evaluated, that essentially allows the attacker to now test words in the dictionary without memory, and now we're back to a problematic custom ASIC attack. Okay, so that's the issue with Scrypt, and so the question is, what do we do about that? Is there a better solution? And so again, there's been progress on this recently. The question that we're kind of asking, is there a space-hard function where in fact the time to evaluate the hash function is independent of the password? And the answer is yes, there actually is such a thing. And here, let me show you. The hash function is called Argon2. and it was actually announced the winner of this password hashing competition that concluded recently. And the nice thing about Argon 2 is it's supposedly space hard, and at the same time, the memory access pattern is independent of the password. So the attack that I just described presumably would be difficult to mount. So the one issue with Argon 2 is there's no kind of rigorous security proof to argue that it really is space hard as is claimed. And so one of the things that we were interested in is basically, can we come up with with a hash function that has the same properties as Argon 2i, but actually has a proof that it cannot be evaluated with less memory than what's claimed? And so the hash function we came up with is called balloon hashing. This is joint work with one of my students, Henry Corrigan-Gibbs, and Stuart Schechter, who is at Microsoft Research. And the properties of the hash function, essentially, as we said, it has a password-independent access pattern, memory-independent access pattern, so you can't do the attack that I just described. It uses basically standard crypto primitives, namely it's just based on SHA-256. So everything here is kind of standardized based on primitives we all know and love. It's actually quite fast and definitely can achieve rates of 1,000 hashes per second. So it can be used on real-world servers. And the interesting property is that in fact it has a proof of security in the following sense. If you try to evaluate it with less space than claimed, in particular, suppose you try to evaluate it with a quarter of the space that we claim is required, then the amount of work to do the evaluation actually kind of blows up exponentially. So if you evaluate it with however much space we said is needed, then you can do it at 1,000 times a second. If you try to evaluate it with a quarter of the space that we said is needed, all of a sudden the total amount of work blows up exponentially. So that's kind of a proof that, at least when it comes to the total amount of work you have to do, that evaluation can't be done without space. So again, if the attacker is trying to build custom ASICs to do a dictionary attack, he has to spend a lot of space to mount the attack. Now, one thing that's interesting is we were primarily interested in the total amount of work that's needed to evaluate the hash function with less space. But it turns out if you're going to build something that has memory access pattern independent of the password, then it turns out there's essentially kind of an impossibility result that says that any such scheme, including Argon 2i and Balloon, is going to be subject to what's called a parallel speedup. So in other words, even though the total amount of work that the attacker has to do has to be quite large, the attacker can still speed up some of what he's doing by kind of laying out multiple cores on his processor. So we're kind of we need to choose between two options. Either we have a hash function where the memory access pattern depends on the password, and then you're vulnerable to the attack that I described before, or you have one where the memory access pattern is independent of the password, but then you have to worry about these parallel speedup attacks. And so what we're actually recommending now is that since we can't kind of have the best of both worlds, let's do both. So kind of the natural thing to do is maybe you use Balloon or Argon 2i to hash the password first. That prevents these memory access pattern attacks. And then you apply Scrypt so that the memory access pattern attack would only apply to the hash password, not the original password. So basically, if you compose Balloon or Argon 2i with Scrypt, in some sense, you kind of get the best of both worlds. Okay, so that's one option to use. So kind of that's what's been happening in the space of password hashing. It's kind of interesting. There's been recent developments, as you can see. So there's lots to say on how to do proper password hashing. This is all very new material. It has not been standardized yet. And so if you're considering moving away from PBKDF2, you should, because PBKDF2 is relatively old at this point. But what to move to yet is actually still, as you can see, a very active area of research. So don't change what you're doing, just wait. Just yet, just wait a little bit more, but just realize that there's actually very active and interesting research going on in the space. I wanted to also show you what the balloon hashing function actually looks like. So, I can't give a presentation without actually giving you a little bit of code. So let me show you what these space-hard functions look like and how they operate. So let's see. So the way they work is basically, as I said, they take as input the password, the salt for the password, the space requirement, and the time requirements. Okay, so what we do is first we allocate a buffer where the password will be that is going to contain the large amount of memory that's needed to evaluate the hash function. The next thing we do is we basically fill up this buffer using values derived from the password and the salt. So what we do is basically, as you can see here, we're kind of hashing the password and the salt, and all we're doing in this loop here is just filling up the buffer using values derived from the password. And we're using, as I said, a hash function here. As you can see, this hash function, this would just be like SHA-256 or so. All right. So then the next thing we do is we're going to do a number of iterations. So this is going to depend on the time cost. So you can see the time cost variable here. The more you iterate, the more secure the hash function becomes in a certain sense, which I won't make explicit here. And then what we do is basically every iteration, we loop through the buffer and do the following steps. Basically, we change, so we take the previous value in the buffer. In other words, we take the, when we're looking at element number m, actually prev is just the value of the buffer element at position m minus 1. And then we hash that, so we hash the element at position n minus 1 with the element at position m. Okay, so we just hash 2 consecutive values. And then in addition, we hash a few more values. We kind of choose 20 more values to hash. And all those values basically form the new value at position m. And as you can see, we're kind of doing a linear scan through the buffer, and at every step in the buffer, we're basically hashing, well, essentially 21 values into this position m in the buffer, and m just kind of increments sequentially one after another. So that's it. That's the whole hash function. We iterate this over and over and over again, and finally the final output is the last entry in the buffer. So it's kind of cool that this hash function just fits on a single page. It's very easy to see how it works. And as I said, most of the work is in proving that, in fact, the total amount of work that has to be done to evaluate this function must take a lot of memory. Okay? So there's an accompanying proof of security that shows that if you try to evaluate this function with little memory, the running time would actually blow up. All right. So that's what I wanted to tell you about password hashing. Now we're going to change gears a little bit. I see that I have 10 more minutes. So we're going to change gears a little bit. I hope in the remaining 10 minutes I can tell you about a completely different topic that we've been working on having to do with control flow integrity. So this is joint work with our students, Ali Mastizeda, Andrew Bitao, a professor here, David Mazieres, and myself. Okay, so let me tell you what this is about. So complete change of gear from password hashing onto control flow integrity. All right. So control flow integrity is a wonderful, wonderful idea due to Abadi et al. Back in 2005. And the idea is essentially it's a way to prevent what are called control hijacking attacks, where the attacker tries to take control of how the program executes. So you know about buffer overflow attacks, return-oriented programming attacks. I hope you know about these things. If you don't know about these types of attacks, please take our secure programming course where we go into extreme depth about all these attacks and how they operate. Okay, so the goal of control flow integrity is basically to protect a program from these control hijacking attacks where the attacker basically is able to essentially take control of how control flow operates, of how control flow flows, and in that, basically that allows the attacker to cause lots of damage to the program. Okay, so there's actually a lot of academic research on control flow integrity. There's actually, there's a lot of systems that I just gave some examples here, and there's also a bunch of attacks on these systems and so on. So this is a very active area of research. Let me tell you, instead of going through all the previous work, let me kind of tell you what this is about, and I'll tell you kind of what we've done. All right, so how does control flow integrity work? Well, again, as I said, there are many proposals. The cool thing is that actually in Windows 10, this has actually been deployed by Microsoft in different systems called MX and Control Flow Guard. Let me just tell you how Control Flow Guard works. So what it does is essentially, what it does, I would say, we consider this as very coarse control flow integrity. But what it does is essentially it builds at compile and linking time. The compiler essentially builds a table of all possible entry points into different functions in the program. Okay, so maybe you have hundreds of functions in your program. Essentially, what the compiler does is it literally lists all these possible entry points all these possible function entry points in a table, it's represented as a bit vector. Yeah, so there's a big bit vector at the beginning of your code that's 0 if that particular address is not an entry point for a function, and the bit vector is 1 if that address is an entry point for a function. And then every time you make an indirect call, so here you can see that you're kind of making an indirect call, say a method invocation or so on. What the program actually does is it takes the address of the indirect call and then calls this extra check here. You can see the check that's shown here. Essentially, this guard check I call, what it does is it looks at the address that the processor is about to jump to, and it verifies that in the bit vector, the corresponding bit is set to 1. In other words, where it's about to jump to really is an entry point to a valid function in the code. So you can't just cause the code to jump wherever you like. You have to jump into a valid entry point in the program. So this makes the control flow, this makes the control hijacking attacks much harder to do. And you see that if this function basically returns, in other words, you are jumping into a valid function, then the actual call takes place. You can see that we're now calling ESI, which actually calls the function. So the call only happens if you jump to an address that's a valid entry point for a function. Now, so this looks great. Yeah, this is already making these control hijacking attacks much harder. However, it's not perfect. When the reason it's not perfect is, first of all, you realize it's checking that the attacker is calling some function, but it's not checking that the attacker is calling the correct function, right? So the attacker can still jump to the wrong function, and that will still cause, in some cases, that still lets the attacker take control of the code, and that's not prevented by control flow guard. So again, control flow guard is a wonderful idea, but you can pretty much see how to get around it by essentially causing the code to jump into the wrong function that's an actual valid function in the program. And the other thing is, why can't we make it more precise? It turns out it's actually non-trivial to build the actual control flow for the program at compile time. It's much easier to do this dynamically at runtime, and that's kind of what we're trying to do. So let me explain to you what we're doing. So we have a different approach to control flow integrity. We call it cryptographic control flow integrity. So rather than building it based on code analysis, we're going to build control flow integrity based on crypto. And so let me explain to you, first of all, what are we assuming? So we're assuming the attacker has a lot of power. The threat model that we give the attacker is we say, the attacker can read and write memory anywhere that it wants. So we're giving the attacker, this is a remote attacker, say that's trying to attack the web server, and we're just assuming the attacker can already read and write any point in memory in this web server, in the web server that's running, that's coming under attack. And in fact, we had a paper actually in 2014, we called this the hacking blind paper, where we actually showed that on a real web server, very often attackers can actually induce reads and writes wherever they want. So it sounds like it's giving the attacker too much power, but we actually came up with attacks where that's exactly the amount of power the attacker has. Literally, it can read and write any point in memory. And even though the attacker has so much power, the attacker should not be able to cause the program to deviate from its designated control flow. So again, control flow must proceed at the allowed, only at the intended flow, and the attacker should not be able to modify that. Okay, so how do we do it? Well, the way we do it is, as I said, using this cryptographic control flow integrity idea. What we do is essentially every time control flow depends on a jump address, we're going to verify integrity of that jump address. In particular, what the code will actually do is every time it writes an address onto the heap or onto the stack, it's going to concatenate to this address a 64-bit integrity tag. Okay, so here is how we compute it. Basically, we're going to depend on the AES block cipher for this. And again, if you want to learn how AES works, we discussed this at great length in our crypto course. But AES is basically one thing that we can use AES for is to compute integrity tags. And what we do is basically we compute essentially this integrity tag on the jump address plus the source address. And we prepend a 0 if it's on the heap, we prepend a 1 if it's on the stack, just so that there's no confusion between addresses on the heap and addresses on the stack. And now you can see that now every single dynamic address on the heap or on the stack is going to have this integrity tag associated with it. And every time we jump to that address, before we jump, we actually verify that the tag is valid. So essentially what the program is doing is making sure that that jump address was actually generated by the program and not by the attacker. So we only jump to addresses that the program generates and not addresses that the attacker controls. Now, you should be asking, when you look at this, you should already be wondering, where is this key K going to be stored, right? I told you that the attacker can read and write any point in memory, so if we store the key K in memory, the attacker can just read it, and once he has the key K, he can forge these tags by himself, and he can defeat the mechanism. So the question is, where do we store this key K so the attacker can't get at it? And the answer is we're going to store it actually in an XMM register. So this key always lives in registers on the processor, and it's never, never, ever written to main memory. So the attacker can't actually read it. And it turns out many programs actually don't use the XMM registers. XMM registers are sort of extended registers in the processor. Many programs don't actually use it, and as long as they don't use it, we can put our key there. Interestingly, OpenSSL actually ends up using the XMM registers, and so to make OpenSSL work with this, OpenSSL is a crypto library. We actually had to do extra work, but again, that's all described in our paper, and I won't describe that here in the interest of time. So just to complete this topic, you must be thinking that we're completely nuts in that, again, if you think about what we're proposing, is every time an address is written to heap or stack, we compute an AES integrity tag on it, and every time we jump to that address, we verify the tag. So if you think about how many times we have to compute AES as the program is running, it sounds like this is just going to have horrible performance implications, but it turns out actually it doesn't. It doesn't. Yeah, so we implemented this in LLVM. We tried this on a lot of kind of common applications, and the slowdown, there is definitely a penalty to doing this, but the slowdown is not like completely unreasonable. There is a slowdown, but it does provide quite a strong level of defense. So how are we able to get this to be so fast? And the answer is, again, something you guys should be aware of, which is, thank you, Intel. Intel has actually made amazing progress in making AES run fast on the x86 processor. So Intel added these instructions called the AES NI instructions. NI stands for new instructions. And what they did, essentially, is they implemented AES in hardware. So there's an AES ENC instruction now that implements one round of the AES cipher. So if you want to do an AES encryption, all you have to do is just call AES ENC 10 times for the 10 rounds of AES, and that's essentially one evaluation of AES. And in fact, as you can see, over the years, Intel has actually made AES even faster as this has been such a successful project for them that AES speed is constantly improving, and the faster it gets, the lower the overhead for our system. Moreover, they even made these AES evaluations fully pipelined, so the throughput for evaluating AES essentially is almost one cycle per one AES round. So this is quite remarkable, and because of these AES instructions, we're able to get the performance for our method to run at a reasonable rate. Okay, so so I wanted to just tell you that these AES, the fact that there's AES available in hardware is great for crypto on the wire, but it's also great for securing applications, for example, by providing this strong control flow integrity. All right, so these are two projects I wanted to tell you about. I guess I wanted to tell you more about Internet of things we're doing, but I guess we will do that at a future webinar. So thanks everyone for the questions, terrific questions. So let's see, let's get to as many of these as we can. So how do GPUs impact the practical implications, ability for evaluating or brute forcing hash functions? So that's a great question actually. So for hash functions that are not space hard, GPUs actually are quite detrimental, right? So again, a GPU has many cores, and as a result, you can actually evaluate many iterations of the hash function at once, and that allows you to speed up the dictionary attacks significantly. So memory hard functions, so functions that require a lot of memory to evaluate, are much harder to run on a GPU, especially because every core, for every evaluation of the hash function, the core has to allocate a lot of memory for evaluating that hash function, and as a result, it's actually quite difficult to do on a GPU. So if you're worried about GPU-based attacks, definitely you need to use a space-hard hash function, like Balloon or Argon or Scrypt, and you should not be using PBKDF2. Generally, I hope I convinced you in this presentation that PBKDF2 is at this point essentially on its way out. Yeah, in a few years, once the discussion of the next generation hash functions is settled, we will not be using PBKDF2 anymore. We really should be using space hard functions. Okay, the second question is basically about having to remember lots of passwords, and the question is about why not use password managers. Of course, password managers themselves also get hacked, so why shouldn't we just get rid of passwords altogether? I couldn't agree more. Couldn't agree more. So, in fact, I'm a very big supporter of second factor authentication. Google Authenticator is a fantastic tool. If you're running a website, you should integrate Google Authenticator into your website to let people use it. You should advertise it for your users. There are even better mechanisms now for second factor authentication, challenge response based. If you're familiar with companies like Duo, they've made that even easier to use. And so definitely I couldn't agree more, and that's a question that's right on target. The next question is how much memory are we talking about? So generally for these space hard functions, whether it's Scrypt, Argon, or Balloon, essentially what we try to do is fill up the L3 cache. So we don't go to main memory, because that actually would not let us achieve the 1,000 hashes per second we're aiming for. But the goal here is to fill up the L3 cache. So when I showed you the pseudocode, the buffer in the pseudocode essentially would be as big as your L3 cache. Okay, let's see. So the next question is about CCFI. Yeah, how would this impact mobile devices? You know, the answer is you could. So I guess on mobile devices you would be using, they're not using Intel processors so much. Those are more ARM-based architectures. So first of all, ARM has also, given the success of AES-NI, ARM has also introduced AES-NI into many of the ARM designs. And so it's exactly the same APIs on the x86. And so in principle, CCFI could be used on mobile devices as well. Any mobile device that supports AES-NI. And my point was that the faster the hardware implementation of AES is, the less overhead that CCFI will take. And it really does provide quite a strong measure of security against control hijacking attacks. And so in principle, this could be used on mobile devices. Again, there's a performance penalty, but there's also a strong security benefit. Okay. The next question is about CCFI on Sparks, and it's basically the same answer I just gave. Essentially, whenever AES-NI is available, whenever you have AES in hardware, you can actually use it without too much penalty, performance penalty. Okay, the next question is about Ring 2. If the attacker gets control of Ring 2 on the computer, yes, absolutely. Then all bets are off. So with Ring 2, you can extract a secret key, and then you would defeat this attack. So the threat model that this is trying to defend against is a model where the attacker has access, read-write access to memory. If the attacker has even more power, then absolutely, that's a much harder adversary to defend against. Then you would have to go to virtualization and other based approaches. Okay, so that's basically CCFI is designed to defend against memory corruption attacks, not so much against Ring 2-based attacks. Can a hacker read-write XMM registers? Yeah, so if a hacker is basically using memory corruption to mount his attacks, then he can't have access to XMM registers. If it's a more powerful attacker, like the previous question, then absolutely, all bets are off. There's no perfect defense. Basically, control flow integrity generally is trying to prevent memory corruption attacks. And we basically were trying to use, our mechanism is essentially using this cryptographic mechanism to prevent memory corruption. Okay, let's see. Are there programming languages, construct compilers that support generation of AES instruction sets? Well, compilers actually don't quite use them today. Typically, when you want to use AES-NI, you would just inject some assembly code into your higher level programming language, and you would compile that in. So, for example, when you use OpenSSL for crypto, OpenSSL actually is, when it's running on the appropriate hardware, it will actually use AES-NI, and so automatically, by using OpenSSL, you're getting the benefits of AES-NI. But yeah, typically you do have to access it using assembly. Is the CCFI project going to be open source? Absolutely. So it's implemented as into LLVM right now. Yeah, we'll make, obviously this is academic code, so use it at your own risk. But absolutely, if you're interested in studying this or using it or developing more on CCFI, we definitely will make this open source. Let's see, on the balloon scheme, where did the number 20 came from? That is an excellent question. I'm really happy to hear someone ask this. So why do we, if you look back to how we did the hashing, we said that essentially as you do your linear sweep through the buffer, you basically hash 20 elements in the buffer into the current element that you're looking at. So why 20? It turns out the number 20 comes from the security proof. Yeah. So this is the nice thing about doing security proofs, in that they guide you into how to design the hash function. So if we do include, if we do the hashing on 20 elements, that allows us to prove that if you evaluate the hash function with less than quarter of the space that we require, the running time would actually blow up exponentially. Okay? So, and by the way, since you asked about the technicalities, I'll tell you that when I say exponentially, I mean exponentially in the number of rounds that the hash function is using. So remember, I told you that there's a timing parameter, how many rounds the hash function runs for. So for example, if you run it for 10 or 20 rounds, let's say you run it for 20 rounds, then if you try to evaluate the hash function with a quarter of the space that's required, then necessarily the running time would grow, the total running time, not the parallel running time, the total running time would grow by a factor of 1,000,000. Okay, so that's where the number 20 comes from. Basically, it's needed for the proof. Right, so you asked about SHA-256. In fact, so in balloon hashing, should we use SHA-256 or a different hash function? So our point was that balloon, that one of the nice features of balloon is it's built from sort of standardized components, and SHA-256 was a very common component to use. In fact, most of our running times, we actually use SHA-3, which is kind of a recent variation, a recent proposal for NIST for a hash function. The reason SHA-3 was better suited for us is because it has a larger block size than SHA-256, and that actually improves performance. So yeah, but essentially you can use any standardized hash function you want. If you want the fastest possible performance, then you would use a hash function with a large block cipher. So just use any of the standardized ones. We just happen to use SHA-3 for running times. Let's see, any research on crypto biometrics or related crypto authentication? Absolutely, there's a lot of research on using biometrics for authentication in a crypto sense. The question is, how do you do hashing when the credential is a biometric, right? So if I have if the biometric is a fingerprint, the credential is a fingerprint, well, when I read it initially, I get one version of the fingerprint. When I read it later on, I get a different version of the fingerprint that might be a little bit different. And the question is, how do we compare the two? Traditionally, when you do biometrics, you kind of extract what's called a sketch from the fingerprint, and then you compare the sketch that was registered from the sketch that was read at a later time. The sketches don't have to fit perfectly, they just have to be close to one another. So the question is, if we do hashing, how do we do the comparison if the sketches only need to be close but don't have to be perfectly equal? And the answer is there's actually something called fuzzy hashing, which actually is relevant for biometrics. Again, so if you're interested in that, just Google fuzzy hashing, and you'll see a whole bunch of papers on how to do hashing for the purpose of biometrics.
Okay, so that's going to wrap up our live session. On behalf of the Stanford Center for Professional Development, I'd like to thank you for joining us for our webinar on hash hack code, emerging trends in cybersecurity. There are still a number of questions in the queue, which we will go ahead and respond to offline. So thank you again for joining us, and have a great day.